Hello everyone, welcome back. Um, I've gotten some comments on my previous video, on the first video I did on the command injection that I found in the Tenda V300 router. One of them was in regards to the audio quality, so I'm hoping that this time around the audio will be a bit better. Another comment that I got was regarding the exploit script that I wrote and whether I've uploaded it anywhere. So I haven't, but I will after this video goes up, and I will be providing a link to that. The point of this video will be to run over to kind of go over the script, give it a little bit of a rundown, to explain how it works, what the different functions do, and what my reasoning was and thinking and design ideas were when writing the script. So let's open the script right here. And all in all, it's um, it's 55 lines of code in total. It almost fits in completely to the terminal window, um, which is really nice. I like it when my exploit scripts are short and concise. They don't need to be more complicated than they have to be. Um, but that's besides the point. So since this is a web vulnerability exploit, which means my payloads are sent over HTTP, then I'll need an HTTP library. And since I'm using Python, my natural go-to HTTP library is the requests library, which I'm using here. I'm importing there. I create a session object since this is a post-auth vulnerability, and therefore, after performing the login operation, authentication cookie is sent from the server to my client, and I'd like that cookie to be saved somewhere. That way I don't have to manually save it myself and send it for every subsequent request. So this session object will do all of that for me. Um, if we skip down to the main function, we can see that the first operation that gets executed is the login. Login function gets called, which currently receives the IP address of the of the server of the host, which is our router in this case. It also receives optional credentials. In my case, the credentials are default, so I didn't bother um, overriding them. Admin. The login function will then MD5 hash the username and the password. I discovered that this is how the credentials are passed to the server by inspecting the authentication flow in Burp. I showed that briefly in the first video, so you can go back and look for that if you're interested in what that looks like on the wire. But this is what this code needs to run in order to comply with that protocol. Um, then what I do is I send a GET request to the login endpoint using the username and password once again with the parameters that I observed again in Burp. These parameters don't seem to do anything, so I just left them with minimal or non-existent values because they don't seem to do anything in this case. The next thing I do is I check for an unsuccessful string in the response text. If this string exists in the response text, that means that the login was unsuccessful. Um, this what this does basically is redirect you using JavaScript to the login page. So that's an indication that you'll need to re-enter your credentials since the first credentials that you sent were not good. Otherwise, the function succeeds and returns true. I should actually be checking here if the login was successful, but whatever, this is a very basic script, so anybody looking to improve it could do so. The next thing is just a simple while loop which reads commands from the stdin and sends them to the server. So the way that the commands are sent to the server is using this run command traceroute function, once again, which receives a IP to send the exploit to send the payload to, and the command that we would like to execute. Um, so as I mentioned in the previous video, I had initially experimented using the NSLOOKUP endpoint, but this version of the exploit does work, but it is not as optimal as the traceroute version. So I left the code in for posterity, although it's unused, as you can see. The function that is used is the traceroute function. And what happens to the command at this point is it gets substituted into this string, which is the actual payload. This is the command injection payload. So the command injection payload starts off with a semicolon, which basically terminates and neutralizes the previous command, which is supplied by the firmware. So that would be the traceroute command itself. So that is basically terminated and neutralized so that it doesn't affect our output. Next up, I run the echo command, and the echo command receives two strings of mine. The first string is padding, what I called padding, and that is going to be 102A characters. This, again, if you'll remember, is in order to trick the firmware into believing that this output is valid. It needs to be of length 101 or higher. So this forces the output to be longer than that. That means that the actual command that I'm trying to run can output 0 characters, but the firmware will find that valid because technically it's printing out 102 A's and then 0 characters. So all in all, it's 102 characters, and that's valid for it. Um, so yeah, so I have to escape. I have to URL encode this whole string in order to be able to send it over HTTP. And then I actually perform the send using the get method, using it straight to the traceroute endpoint, and the payload gets inserted into the hostname parameter, which is the hostname that is supposed to be trace routed according to the original functionality of this diagnostic tool, of the traceroute diagnostic tool. Once the response is received, I parse out the actual command output using this simple regex. What it actually does is it searches the response text for this string, which is part of the JavaScript in the HTML that is returned to the client. After this OK, the traceroute output is supposed to appear. In our case, what we'll receive is our padding, because that is what we echoed first, and then a space, which is what we echoed after the padding, and then directly after the space, the command output. So I use a named capture group, or a named regex capture group, to capture the output. I called it output, and that way here I can just uh, query that. I could access that group, that substring from the server's response, and that'll contain the command output that I'm actually looking for. Now that command output in the firmware has been manipulated. All the break lines were replaced with tilde characters, so here I have to replace them back to break lines. And once I've done that, I just print it out to the console, and that's it. The vulnerability has been exploited, the response has been received, printed out, and effectively, as far as this prompt goes, a command was received and run remotely and then printed back out. So that's it. The next iteration is run until the exit instruction is given, and then that breaks the loop, which terminates the script. One thing you'll notice is this exception, um, which seems to happen when running into what I'm assuming is a Stack Overflow or some kind of buffer overflow issue, because once again I'm playing around with the length of these of the functions on the back end, the C functions that I looked at in the last video in the firmware. Um, so so in some cases when that happens, the router kind of stops. It kind of freezes up and requests throws an exception, like some kind of timeout. I don't remember exactly what it is, but I just did it. I added this to the script to kind of gracefully handle that and quit quietly without some kind of weird HTTP error. So it's not very critical, but because in any event, if you reach this part of the code, then the router is not functional. It's rebooting or whatever, so you won't be able to run any more commands. So the script will exit in any event, and you'll just have to rerun it once the router is back up and running. Um, and that's basically it. As I said in the beginning, I will be uploading this script to somewhere, so you can look for the link in the description of this video. Thank you very much for watching.